Hello, in this lesson, we're going to talk about how to solve simple logarithm equations. Before we do that, we'd like to recap on the domain and range of logarithm functions, right? We have studied these functions and we understand the relationship between the logarithm functions and its inverse, right? So logarithm function base 2 and its inverse 2 to the power x. One's domain is the other's range and vice versa. So these pairs are being studied by us in the past, okay? Understanding the domain and range relationship is super duper important as we move forward with our solving logarithm equations, okay? Logarithm equations. And in this section, of course, we're only going to talk about solving simple logarithm equations. And in this relationship, right, we understand the correspondence. We understand the correspondence, right? From the general form of log base b, okay, of omega equals to triangle, right? So that's we are heading towards the definition, right? So b raised to the power triangle is equals to omega, right? And of course, all the bases we're considering is going to be larger than 0 and not equals to 1. So in this relationship, in the special cases, it describes for base 2, right? For base 2, when b is 2, right? So that describes the relationship between logarithm base 2 and 2 to the power x. And for base 3, and that describes the relationship between, that's triangle, right? Base is 3, right? And in the case of natural log, right, base e, and we have base e here, and the shorthand notation is ln, okay? And last, of course, not least, which is also commonly used, is a common log base 10, right, base 10. So this is 10 to the power triangle. And by default, we use log to represent common log, right? So this is a general form. And these others are special cases. And of course, we can create special cases for any base as long as the base is larger than 0 and not equals to 1. Graphics, right? The graph. And here I have the graph for exponential functions and logarithm function. Let's see what they are. If we can still tell their relative positions. Okay, I did this graph ahead of time. So this time I'm just going to remove it. Okay, so I'm going to do it by removing, right? So you know which one is log base 2x, right? So delete it. Log base 2x, it was the one, right? And 2 to the power x removed. So that's the log base 2x and 2 to the power x. And the next one I'm going to remove is base 3, log base 3x, and 3 to the power x. Okay, and the last one, of course, is e to the power x, ln x, which is the red one over here. And the next one is going to be e to the power x, right? So these two are e to the power x and ln x. So let's put them back in. Okay? Log base 2x. Okay, so for that pair, we're going to use the color of, maybe we should just use purple, right? We just use purple. And 2 to the power x. So this pair, okay, this pair, purple. Oh, We should have them the solid, okay, not a dash. Okay, solid. Okay, 2 to the power x, solid. Okay, and then you may like to guess. Next, we're gonna do log base 3x, right? And what color shall we take? Let's take the color blue, right? And 3 to the power x, so this pair that are inverse function to each other, right? Inverse function to each other. There you go, the blue. Oh, broken again, sorry. I meant to have them to be solid. Okay, it should be solid, my bad. Solid, okay, and a solid. There we go, solid. Now we're gonna plot 10 to the power x and common log x. Where do you think they're going to be? Where do you think they're going to be? Okay, so let's review what we have seen. What we have seen, right? The blue, what is the blue? What is the blue? We can see these pictures, right? How do we identify which one is which? We can put some points in there. We can put some points there, right? For what are the points on 2 to the power x? The point on 2 to the power x, if you have 1, the output will be 2, right? So where would that point be? Where would that point be? So I suppose I put the black dot there. So this point is going to be on 2 to the power x, right? And there we go. Where is it? 1, 2. Where? Oh, you know what? I have not selected the point. The point. There we go. So this purple is 2 to the power x. And this other purple is log base 2x, right? How do I know, right? So when we identify which curve is which, right? So we're going to choose some points. Okay, so I'm going to put a little table there. Okay, that should be sufficient, right? So for 2 to the power x, right? And log base 2x, right? We've plotted those points. We've plotted a lot of those points. So with that, we know that the point, right? So I'm going to put this over here. So if you look at the point, okay, point, right? Or points, right? If x equals to 1, y equals to 2, right? For log base 2, if x equals to 2, y equals to 1, right? Because 2 to the power 1 equals to 2. Log base 2 of 2 equals to 1, right? So we can do the same thing for 3 to the power x, right? So we don't need so many. We just need to identify them, right? So for 3 to the power x, we can do the same thing, right? For 3 to the power x, what will happen? Log base 3. Well, x equals to 1, y, the output is 3. So this will be 3. 1 input is 3, output is 1. So these will help us to separate which graph is which, okay? So now suppose I like to know, oh, 2, 1, right? This is a point that is on the log base 2x, right? And then I just gonna see where that point is. So identify the point. So these two curves, right? So by this time we have identified this piece is 2 to the power x, right? And that piece is log base 2x. And we got it, right? To keep what we've discovered, right? How about we change the color, the black dot, to be the same color as the curve, right? So that will make it easier for us. So that's what I'm going to do. So I'm going to change the color of the two dots to be the same color, which is purple, right? We're chosen to be purple. And I'm going to choose it to be purple. And those has been identified. Very good. So that's 2 to the power x, right? So we use the color what? Purple. Documented, right? The next one is 1, 3, 3, 1. We'll do the same thing. Okay, so I'm going to plot the dot. We're going to plot the dot. Right? At first, we just put it as black. Okay. And 3, 1, 3, 1. And there we go. We get these 2 points. And there, it looks like, oh, wait. There's another dot. 1, 3 is not showing, right? 1, 3 is not showing. Oh, that's because I didn't put the, there we go. Okay, it looks like it's on the blue, even though it looks kind of, it's actually on the blue, right? So that is going to be the blue. And that blue, now we're going to change those colors to be blue, right? So that we can have a reference, right? So this is going to be blue. And that is going to be blue. So what I'm trying to show here is that when you identify curves, you can use points to identify them. And of course, the last one is going to be e to the power x and ln x. E to the power x and ln x. Okay, so that's the red. Okay, to confirm it, we're going to be doing the same thing to confirm it, right? So when input equals 1, that equals to e. When ln e equals to 1, right? So we're going to plot these 2 dots on the curve just to confirm which one is our ln x and which one is our is the point on our curve, right? So this one is going to be e, 1 is going to be e to e, 1. So there we go. We got the point, right? So look at they're on the red. Okay. So with this observation, of course, I'm going to change the color on the red curve by the red color. Okay. So it's just a way to organize. Okay. So now we can mark these safely. Right? The blue is 3 to the power x. So I'm going to use blue color, 3 to the power x. So that is a 3 to the power, this is a log base 3. So that blue is log base 3 x. The purple, what will be the purple? The purple is 2 to the power x. 2 to the power x. Okay, so the purple is log base 2x. Color coordinated. The red, right? The red, of course, is e to the power x. E to the power x. And the red over here is ln x. With these observation, and we also know that, right? 2 is less than e, less than 3. And if you are graphing 10 to the power x, okay, and log x, common log x, where do you think they're going to be? You guessed it, right? You guessed it. So we've seen the pattern, right? For exponential function, base 2, base e, base 3, the curve is getting steeper and steeper, at the slope is getting larger and as the base getting larger and larger. The logarithm, however, right, as the base getting larger and larger, the curve is getting closer, getting flatter and flatter, which is getting closer and closer to x, right? So with that, let's confirm if our observation is correct. Okay, so I'm going to plot 10 to the power x. We're going to see if that is in agreement with your and mine educated guess. Okay, so this is 10 to the power of x. See, that's 10 to the power x. For some reason, I always get a dash line. No, I don't want to get dash line. I get a solid line. There we go. So 10 to the power x. So you can see that fits the pattern. How about a common log x? Common log x. Common log x, of course, is going to be ln x here. It should be the lowest among all of these. Okay. And I think this software may have some problem. So I'm going to do a change of base, ln x log 10, ln 10. Okay, so this should give us the right picture. This should give us the right picture. There we go. That's a 10 to the power. That's a log base 10. Okay, so this is black. This is black. Okay, and this is a 10 to the power x. And this black here is log 10, log x. Okay. Obviously, I think this software can only graph ln x. It doesn't graph log x, but that's okay. We can use change. I just use change of base to modify that to make it happen. But anyway, without further ado, you can see all 4 functions which are commonly used, and other functions will be similar. You can find their places. If you're given 5 to the power x, where would it be? It's going to be between 3 to the power x and 10 to the power x, right? And the log base 5x is going to be between the blue and the black. So these are the patterns we have discovered. Of course, today's lesson is about solving simple logarithm equations. In other words, we know the output and we're looking for the input. Okay, we're looking for the input. So without further ado, let's just clean this up, and we're going to look at some, logarithm equations. Domain range, are we clear about domain and range? Are we clear about domain and range? Yes. Here we go, right? We have studied domain and range, right? And the domain range was summarized earlier on this picture, right? So they all have the same domain and same range for these functions. They have the same domain, right? And same range, right? Same domain and range. So once we're clear about these relationship, okay, so next we're going to look at some equations, okay? These kind of equations is also, titled typically solve for x. Solve for x. You may like to look at the homework questions I have there in the, let's look at some homework questions. Okay, hold on a second. I'm going to stop the share. Okay, I'm bringing up the homework questions. Okay, I'm going to bring up the homework questions. Hold on. The homework questions is where we're going to start, and then we can tweak it. Yeah, I turn off my computer, so I don't have to re-log in. One more questions for week 10. Week number 10. Okay, so now I'm ready to share with you. So let's look at these homework questions. We have covered the majority of these questions in our other lessons this week. So and today we're going to look at these questions for number 8, solving the simple logarithm equations. Okay, so I'm going to put these as on the side, and so you can take a look at it. You could have access to it while you're watching. Okay, I'm still going to go back to our lesson, Okay, so solve for this. Let's look at the first one. The first one says log base 2 of x is equals to 3. Okay, first of all, what does it mean? I'm going to talk about the different methods we can use, we can use. Okay, always be aware of domain and range, because domain tell us, what kind of value can be used as input, and the range tell us what can be expected, right? Anything outside the range, it cannot be expected, right? As we saw many examples in solving exponential equations, right? But anyway, now, excuse me, okay? What does this mean? This means that we have a function. And the input to that function is x. Okay, so we should assume, because we know the domain of a logarithm, right? So by this time, we should know that the solution, even though we don't know the solution, we know the solution is going to be positive. And we know the output is going to be 3. So we must understand this, okay? We must understand this. Anything we give as input to this function must be from the domain. If it is not from the domain, what do you say? It's undefined, right? And then that's the end of it. And in this case, we don't know what's the input, but we know the output. Therefore, we are looking for that output. We talk about methods, right? The function method, right? The first method is a graph, because we know the graph of log base 2x so well, right? We know the graph of this function so well. And then we just draw a horizontal line for the output, right? So there we go. And you can see the similarity between what we do here and what we have done with the other, equation questions, right? Other equation questions. So here we go. So this is the graph, right? This graph, we know how to read it, input, output, right? Input is horizontal, output is vertical. We don't know the input, we're looking for input, and we need to find output. So how do we find it? Well, we're going to draw a horizontal line. 3 is the horizontal, is the output. So we're going to draw a horizontal line, y equals to 3. And y equals to 3 has a crossing. Okay, so we draw the line y equals to 3. We have done this similar. So there's a crossing. How many crossings are there? 1. That means we're going to have only one input for that output. Okay, so this graph, this crossing tell us there's only one solution. So this crossing tell us, okay, so let me write it down. Okay, there's one crossing. crossing, okay, for y equals to 3 and logarithm and log base 2 of x. There's only one crossing, okay, only one crossing. What does that mean? This tells us there is exactly one solution to this equation. Not a 2, not a 0, exactly one solution. Exactly one solution. And if you can read the value from the graph and you found it, right? So this is going to be x, right? So let me use the color to indicate x, right? This is x, right? It happens so that in this time we can read the graph. You understand, sometimes we cannot read the graph to get the precise value, but this time it happens to be so because everybody probably know this answer, right? The answer is 8, right? So this crossing, this point, tell us the input such that the output is 3. Okay, so this is the context and this is the function perspective we have been repetitively talking about. No matter what the rule is, whether it's a trig function rules, arc trig function rules, or any function, this is the basic. This is the very basic, right? And of course, I can plot the points now, right? I can plot the points now, and that point tell us the solution. So 8, 3. And that dot tell us that dot, right? And we can even mark the dot. We can even mark the dot. 8, 3. Okay. And we're going to put 8. And here we're going to put 3.25 to see if that will make a proper show. Okay, let's try it. 8.3, 8.3. Okay, so that's input, output. We're looking for input from given output. You see, that's the essence of solving equations. Okay, so but this method, you can see it has pros and cons. The graphing method is not always taught in a lot of textbook. Okay, in a lot of textbook, we go straight to the algebraic method. But when we do the algebraic method, you have to be aware of domain and range, right? But with graphing tell us things that are very visual. How many solutions could be expected? Okay, sometimes we can tell from the graph. In many cases, we can tell how many solutions are expected and where they are possibly be, or what is the neighborhood, what are the likely numbers. Sometimes, in most cases, the precise value is very difficult to identify. So that is the shortcoming. That's the shortcoming of the graphing method. Okay, for that reason, the graphing method is not used very much. But since we cover this course from functions perspective consistently, so I always want to give you that function perspective, okay, from the input output. So this way you can see from all these different rules, right? The only difference is the rules are different. The ideas and the approach of function method actually are very, very similar. So now let's look at method 2. Method 2, of course, is algebraic method, right? So we know that log base 2x is equals to 3, right? So by definition, right? By definition, oh, sorry, let me clean this up. Okay, by definition, we use definition, so x would just be equals to what? 2 to the power 3. Okay, so the definition we quoted, right? We've said that at the beginning. This is these are the definitions, right? And the definition we have cited, right, is this one. So that's the definition. That's the definition. Okay. And that's it. So in terms of showing work, I would say you just show these two lines. Very simple, very simple. That's how you need to show work. If you want to show the graph, great, right? If you want to show the graph to demonstrate you understand it so well, that's even better. That's great. Okay, so let's look at another question. The next question you're going to see is actually log. Oh, let's make it x, example number 2. Okay, and in this question, we have log base x of 3 equals to 2. So the unknown we're looking for is x, but x is at a position of the base. X as a placeholder, it holds the place of the base, right? Since we don't know the base, we actually cannot use a graphic method. We cannot use a graph because we don't know the base, right? We don't know the base. We still know the output is 2. We know the output is 2, right? So naturally, you're going to, you can still use a base, except that you have to graph a lot of graph in order to make that a match. Okay, so that's too much work. So what I would do is I will use definition. From definition, since we don't know the base, and I'm gonna use this one as definition, right? I'm gonna use this definition right here, right? So I'm gonna do some think out aloud. Right? So this is what I have. So basically this is what I write down on the scratch paper, right? So I just put numbers in places, right? I just put numbers in places. Okay, it tell me the base is unknown, right? Base is B, right? B space is X, and this is a base. Triangle is 2, so triangle is 2. Omega is 3. Omega is 3. There we go. Right, so from definition, right? So from definition, you can say from definition, from definition, right? From here, I got x squared equals to 3. I got x squared equals to 3. Okay, if x squared is 3, and of course you can use a graph to identify, right? You can use a graph to identify, right? Such that, so this is a statement, right? X squared equals to 3. And the function is x squared, right? You can use that. So x squared. That graph is parabola. We're very familiar with it. Okay, that's x squared. It equals to 3. You can see the same idea, right? The same idea. So let me make some adjustment to the picture. Okay, and over here, I'm gonna make it 7 is good. Okay, all right. So now for solving this equation, which is, we also know the output is 3. So we're gonna draw the horizontal line equals to 3. Right? And there are two crossings. There are two crossings. What are the crossing? So what are the input output at each crossing? And we can easily identify them, right? We can easily identify them. So there's a negative one number, there's a positive number. It's hard to recognize. It's hard to, because the number is going to be between -1 to -2. This is one between 1 and 2, right? It's hard to identify this number, but we understand what this is, right? So we understand that we are having two solutions, right? One solution is this piece, right? It's between 1.5 and 2. And the other number is on the other side, and they're opposite to each other because this, x squared is an even function. Other than that, we know we expect two solutions, but we also know it's very difficult to identify the solutions, right? So next, we're gonna reach out to use our algebraic method. Okay, I will show you at the end. Okay, I will show you at the end how we're going to approach this. So I'll put all of these as think out aloud, right? All of these as think out aloud. Okay, so we don't need this anymore. I will show you later. Just after we're done analyzing, think out aloud, we know there are two solutions. Algebraically, we have very sophisticated procedures for these, right? What do we have? We'll take square root on both sides. Okay, we take square root on both sides. Root 3. Whoops. Okay, root 3. And the left-hand side is absolute value. Absolute value. Okay, so the absolute value of x equals to 3. And we know that, the number we want to identify, those are actually negative root 3 and positive root 3. So at this point, you recognize, so x is equals to plus or minus root 3. There you go, right? We found two solutions. Okay, so these two solutions are negative root 3, comma 3. And the other one, okay, so let me put the red dot here. And the other one is positive root 3 of 3. These are the two dots, right? To which equation? To this equation. We have two solutions, right? So to read the graph, we realize, this number, right? This is a root 3, right? And that's a negative root 3. Okay, and they both have the same output. The output are 3. So you can also mark the point. You can mark these 2 points, right? The 2 points would be root 3 input, and output is 3, right? And this point would be negative root 3, and the output is 3. Do you see a lot of similarities when we handle, functions? But the question is, this x we found is going to be used at the base of logarithm. So I'm going to clean this up, right? We're looking for x for sure. And we ended up with x squared equals 3. And we find two values for x. Okay, the x as the base of a logarithm cannot be negative. Remember, we emphasize the base must be what? The base must be larger than 0 and not equals to 1. Not equals to 1, we get it, right? That's satisfied. But it cannot be negative. It must be positive. Well, then our solution to the question x playing a role as the base of a logarithm. Okay, so in the end, right? You say as a base for logarithm, log base x, right? Of whatever. X must be what? X must be larger than 0, not equals to 1. Okay, so in the end, the solution, x will be equals to positive root 3. Negative root 3 will not be the solution. Okay, so now let's wrap this up. Let's put this together, right? Then you say, how much work do I need to show? How much work I need to show? Okay, so this is what you will show. I will show right here, okay, show work, right? So let's do show work part. Show work part, okay? I will say by definition, okay, we got x squared equals to 3, okay? And then we go through these steps. Solving for x. And then in the end, you say as a base for logarithm, right? As a base for logarithm. And that's how much work you need to show. Okay, that's how much work you need to show here. Okay, of course, you're going to remove the show work part. This is what you're going to show work. Okay, show work. How much you need to show? This much. Okay, so first part, you know how to solve equations of this sort. Secondly, you understand the base for logarithm has to be larger than 0, not equals to 1. So this entire piece reflected your understanding for both. And that's cool. And you're going to get points accordingly. Okay. And these analysis, including the graph, you don't need to show them. You don't need to show the reader. Okay. Of course, those are yours, right? Let's look at another example. Example number 3. Okay, in this example, okay, we have a log base 2 of -5. Oh, wait, log base 2. Wait, I made a mistake. You know what? I need to change that. It should be log base 2x equals to -5. Hold on a second. Okay, I need to change that typo. Something was missing in my typing. Okay, thank goodness I found it before I publish it. Okay, so that there's need to be an X, my bad. Okay, there need to be an X there. All right, so that's been corrected, saved before I publish. All right, here we go. We're solving this equation. Of course, you can use a definition, but I still want to show you the function perspective. Method 1, graphing, log base 2x. Log base 2x, we graphed that before, right? We graphed that before. We did. Right? In that before, it was for different equation, but this time the output is what? The output is x. Okay, the output is x. The function is such, right? We have the graph, and the output is -5. So when output is 3, we graph y equals 3. When output is -5, we're going to graph what? We're going to graph y equals to -5 as a horizontal line to cross the curve. So all of these need to change. What is more, we anticipate we anticipate that the solution, okay, the x we're looking for must be from the domain, okay? X, the solution must be positive, okay? Which is from what? From the domain of log base 2x. This is the importance of domain and range. So they're omnipresent. They're omnipresent in every step of the way. In every step of the way, we need to refer to them in order to make sure we get the absolutely correct answer. Okay, so this picture, of course, needs to be adjusted. The picture needs to be adjusted, right? The picture needs to be adjusted. So I'm going to, instead of drawing 3, I'm going to draw -5 horizontal line. It doesn't show. Why? Why doesn't it show? Because I need to adjust my view, right? So I'm going to have a -6. Okay. And here I'll maybe make it low, a little bit lower, right? So here. So now my y equals to -5 will show. And this point will have to be gone. That point will have to be gone. So I'm going to remove that point, okay, of 8, 3, right? It's not needed. And the marking is going to be removed. Here we go. And this time there is a crossing. So let me just expand it a little bit. Now we see better, right? So this line, this horizontal line, okay, let me mark it. This horizontal line we just draw. Okay, this horizontal line we just draw is y equals to -5. Y equals to -5. So I'm going to draw, I'm going to put it at 2, -4.75, right? And the horizontal line crosses the curve. The horizontal line crosses the curve. How many places it crosses the curve? 1 place, exactly 1. So this is the point of intersection. And this point of intersection, okay, this point of intersection tell us what? Tell us what the x is. They tell us the input and tell us the output. The output, of course, is -5. Okay, so this point of intersection tell us where is the input, what is the input, what is the output, and what's the input. So let's look at the visual of this input. The input, the visual of this input is really just a very small number like that. Okay, and the output, okay, the output is this much. Okay, we don't know the input. Okay, we pretend we don't know. Some of you probably already figured out, right? So this is the output, -5. And that's that little black there, that's the input we're looking for. You see, that has to be positive, right? X has to be positive. X must be positive. It has to be from the domain. It has to be from the domain. That's the important points we're making here. Okay, that's the important points we're making here. Okay. Now, of course, it's very difficult to guess that point, but we have the visual. We have the visual. We can see how it is. The whole thing is consistent with our analysis about these functions. Okay, we don't know the answer yet. We don't know the answer yet. So I'm going to move forward to use the algebraic method. What is the algebraic method? Right? What is the algebraic method? By definition. By definition. Which definition would apply to our case? Right? So this is a method 2. Method 2, right? We look at the definition. which is right here, right? Logarithm, right? Omega is x, x is what we're looking for. And obviously we can get x very easily. X equals to 2 to the power of what? -5, right? By definition. And that's all you need to do, really. So most of the textbooks just teach you this part. Okay, most textbooks just teach you this part. Few of them will show you the picture. But I think showing and understanding the picture is super duper important as well. Okay, so however, on the work you show to any professors, including myself, if you ask to solve this equation, you just show this much work, and to me, that's perfect. But if you can understand its position, if you can understand the graph, and even make a connection to the graph, then you have gone deeper, and this is going to benefit you tremendously. Okay, so now I'm going to plot the point in the picture. Okay, the point is plotted. Okay, it is not on y-axis. Okay, but this is just a point, and this point has the, you know, the little x there, right? That's the little x there we just drew earlier, right? That little piece, very little, okay, because it's 1 out of 32, right? 1 over 32. And the y, that's horizontal, right? The vertical is a -5. So this is -5. So this is y equals -5. That's the output, input, output. That's what I want you to understand. So once again, if you know how to do this, great. If you can understand this picture and the whole thing we covered consistently, repetitively, that will be even better. It will serve you very well for your future calculus classes. Okay. Now let's look at a few other examples. Okay, I'm going to do some ease. Okay, I'm going to do some other examples. Okay, and involve some fractions and so on and so forth. Okay, because I know some of us has hard time with you know, fractions. So example number 4. And this question goes like this: log base x of 5 is equals to -12. We don't know the base, so graphing method may be maybe too much work. It can be done, but it could be too much work. Why too much work? Because you don't know which base, right? For every base, you get a picture. So you kind of hit and miss, right? And especially that you don't know what the answer is going to be, right? So we're gonna opt to use algebraic method. So when we use when we don't know the base, we just use the definition in the general form, right? So by definition, right, x will be x raised to the -12 power is equals to 5. Okay, x is raised to -12 power equals to 5. So that's what we get for by definition. And from what we have addressed earlier, x is a what? X the base of a logarithm, and x must be positive. We don't know the answer, but we know what to expect. We know that x is going to be positive. The solution must be positive. Okay, so we're going to solve this equation. Solving this equation. How do we solve this equation? Right? What does that mean? Well, that just means 1 over, oops, what am I doing? That just means x raised to the power of a negative half equals to 5. Okay, remind you of like b raised to the power of a negative n is equals to 1 over b to the power of n. Okay, that's where it's from. If you need to pause to figure this out, go for it. And of course, x raised to the power half is equals to what? It's a square root. So this is actually square root of x. 1 over square root of x equals to 5. Okay, x. And we're looking for x. So how do we solve it? How do we solve it? Well, we can flip over on both sides, right? There's no zero involved. We don't have to worry about it. So we get square root of x equals to 1/5. Equals to 1/5. Okay, and then we're closer to x, aren't we? Because if we square both sides, right? And what is the left-hand side? So we square both sides. And the right-hand side is 1 over 25. And the left-hand side, what does the left-hand side equal to? The left-hand side equals to x. Okay, so x equals to 1 over 25. Okay. Here, I want to put a little note here because I sense that some of you might be confused. Okay, some of you might be confused between this thing, this expression, and that expression. We did talk about this before, but I think it's worthwhile to talk about it again and again. What's the difference between these two expressions, which you guys get to use them very often. They show up very, very often in your future work in calculus, which is any basic algebra. You see these very often. Okay, now what's the difference? Big difference. Big difference. Okay, if we look at these two, right? This one tell us it's actually a rule. This one is another rule. We can see them as a rule. Okay, these are two different rules. Once we're talking about rules and we're talking about functions, aren't we? Right? So this rule says by order of operation, you're going to have x as input, and then you're going to do square root of x first. Okay, after you get the square root of x, and you square it. You square the result of square root of x. Okay, at this step, right? At this step, because x is going to be applied the rule of square root, so it has to be in the domain of square root of x. And that domain is going to, we talked about that before, x greater than or equal to 0. So by using this rule, by default, x has to be greater than or equal to 0. Okay, so as a result, the consequence is going to be the same as x. So we started with a non-negative x, we ended with with x. Therefore, this expression is equals to x. Okay. The other one, however, right? You're gonna have x. Wait. Okay. X is the input, and then you do x squared. Right? After you do the x squared, then you take a square root. Okay, that's the order of operation. Now, this second rule tells us that it doesn't matter what x is going to be, because the rule you apply is x squared, right? And the domain of x squared is all real numbers. All real numbers. So x can be positive, negative, 0. Okay? So the domain for x squared determines the input can be positive, negative, or 0. Okay, so x can be any real number. X can be any real number. And therefore, this result, okay, we discussed, we have studied these before, right, is going to be equals to absolute value of x. Okay, so that's the difference between these two expressions. Okay, you must understand this. You can see the domain plays a fundamental role, and the order of operation plays a fundamental role in this case. You can see it's all about function. It's all about function. Okay, so that was our note. So let's go back to our question. Did we solve our question yet? Did we solve our question already? Yes, we did. Okay, for a question, for this particular question, and these are the work you need to show. These are the work you need to show. In other words, the base. Okay. Okay. So this is the side story then, right? That is, if the base is 1/25. 1/25, and log base 1/25 of 5 equals -½ Okay, and that's not hard to verify, right? So that's not hard to, if you check the answer, you will realize, you know what? And this piece and the 5 equals to square root of 25, right? 5 equals square root of 25. And therefore, for log base of 1/25, and over here is just 25 to the power of what? Half. Oops, half. Oh, wait. Okay. All right. And better yet, right? The base is 1/25, right? The base is 1/25. So what you're going to do is that you're going to do 25, that's 1/25. Okay, just wait, okay, to the power of -1. To the power of -1. Okay, that's how you get to log base 1/25. I know it's a lot of algebra around here, right? And inside the parentheses, you have 1/25. That's one way to check it. I will show you the change of base formula. So that's -½ if you don't like it this way, right? Of course, that you can check the answer. The answer is -½ right? These work, if you can do, that would be great, but usually it's not required of you. But I'm showing you this, it's just really for the fun of it, but it does improve your algebraic skill, okay, trust me. So if we can verify this by doing what? By change of base, right? By change of base. We decide we're going to change the base to base 5. How about that? I'm going to change the base to base 5. Log base 5. Right? And the old omega is 5. And the next one, the old base is 1/25. 1/25. So the top equals to 1. The bottom equals to log base 5 of 1. I'm using quotient rule, and log base 5 of 25. So you still get log base 5, of 1 equals to 0. So you still get a, and so you're gonna get a 1 over 0 minus 2, and you get negative half. You can see there are all these ways, and you get to practice how to manipulate power, how to use the change of base formula. Practice, sometimes those exercises, you can invent some exercise yourself, okay? And surely I give you, I give you homework, but this week it's actually excessive, right? I give you more questions than I used to, because I know you can do it. You can do it. These exercises are very, very important. Okay, very, very important, because I saw too much lack of exercise when you do calculus, because of deficiency we had from algebra that really has serious consequence for your grades in calculus classes. Okay, so I hope this will help you, okay, to do more and more exercise so you'll be better prepared. Okay, so that's example number 4. Let's look at example number 5. Okay, so example number 5. Okay, this example I choose is going to be natural log. Okay, ln x equals to 3. And this is rather straightforward, right? This is rather straightforward. Graphical method, right, or algebraic method. I do want to show you the method, the algebraic method, especially because it's oftentimes not being taught. Okay, oftentimes it's not being taught. So the understanding is that we have input. The input is x, right? The function processes it. The output is 3. The output is 3, right? And therefore, we're going to graph ln x. I'm going to draw a horizontal line, right? What do you discover, right? Because the output, because the range of ln x is from negative infinity to positive infinity, I'm going to write it down, okay? I will write it down. In most of those cases, you have solutions, okay? So hold on, let me put the view properly. And here I'm going to put 8. And right here, I'm going to put -3, maybe 4, right here. Okay, ln x, right? The range is from negative infinity to positive infinity. So in terms of this type of equation, you always have solution, right? It doesn't matter. You can see I have examples in the homework, right? The output can be negative number, positive number, negative fraction, positive fraction, any number you wish, right? There are solutions. Okay. After all, for exponential logarithm, there are only 3 quantities, right? Base, exponent, and the power, right? So it's all about these 3 quantities. If you figure out about these 3 quantities, the base cannot be equals to 1, must be positive, right? And after you've taken the power, it's always positive. So omega must be positive, right? So number at this position must be positive. And the power itself can be any real number, okay? Just figure that out, okay? You need to think about it. So the output is 3, so we're gonna draw a horizontal line, y equals to 3, right? Y equals to 3. And sure enough, there's a crossing, but this graph doesn't show the crossing. Does not mean the crossing doesn't exist. So you have to, I just have to make it longer, right? So it crossed, right? Maybe I put 25. There you go, so it crosses somewhere, right? Because you know it's vertically from negative infinity to positive infinity. You draw y equals 3, it's going to cross it. Okay. So what is the point of intersection then? What is the point of intersection? So you have to guess the answer, right? We have to guess the answer. What is the answer? It's very difficult to guess this answer in this case. We can only tell from the graph. Okay, we can tell from the graph. What can we tell? What can be told from the graph? There is exactly one solution. What is that one solution? Right, there's a touch, right? No touch, no solution. If there's a touch, there are solutions. It's just a matter of how many. Well, ln x is a one-to-one function, right? It's a one-to-one function. In other words, it is also an increasing function. Well, there's one solution. So this tells us how many solutions to be expected. So function method and with the help of graph really tell us a lot of information. I really think that we should do more of these instead of less of it, right? But anyway, so we still need to look at the algebraic way. So that's why most of the textbook will teach us the algebraic way to solve the equation. Okay, so the graph way is not often taught because maybe because you only have so many pages, right? So the answer actually is e to the power of what? 3. And which definition is it fitting here? The definition we can apply here is this piece. Whoops. Okay. ln. Okay, definition. How much work you need to show? You really just need to show this much. Okay. On textbook, you typically would just see this. You're less likely to see the graph. I show you the graph and I want you to really understand it. You must commit yourself to understand it. If you want to really lay a good foundation for yourself to do well in calculus class, okay? So now we got the point. Right? The input is e to the power 3 and the output is 3. The red dot right there. So the algebraic method give us information, right? It gives us better information about the actual value itself. So e to the power 3 is the input and the output is 3. I think with this understanding, with this much understanding, your understanding is complete. Your understanding is complete. Okay. All right. Let's do one more. Okay, let's do one more. This one more, which will be example number 6. Is that number 6? Is that example number 6? Yes, example number 6. Okay. We have a ln x equals to 3/2 fraction. Now, what will be the answer? Well, the answer would just be x equals to e raised to the power of 3/2. That's it. E raised to the power of 3/2. Okay. Did I do -half? No, we didn't. We're going to do a negative number for ln. Okay. And we got the graph, right? I'm going to borrow this graph So you can see the similarity, right? In the previous case, the output is what? The output was 3. And now the output is 3/2. So I'm going to have to redraw that picture, right? The output is 3. So now it's 3/2. Same idea. So the solution, right, exists. The solution exists, but this time is somewhere else. So are they similar questions? They are similar questions, aren't they? Whoops, the red dot. Okay, the red dot, I didn't plot properly. Okay, it's a 3/2. 3/2 right here. Same type of question, Okay, so in terms of showing work, this much is more than sufficient. Okay, but if you understand the whole picture, it will be so much better. Okay, so the last one, I think I'm gonna do the last one for you. Okay, so this one is ln x equals to -1/2. -1/2. Algebraically, right? Algebraically, what does that equal to? Well, x just equals to what? E raised to the power of what? -1/2. Which is 1/square root of E. Okay. And if you want to rationalize it, you could do root E over E. Okay. I trust you guys can do this. If you have any questions, let me know. Graphics, the graph, okay. The visual. This much work, you're done, you're good. Okay, but let's try to understand a little bit more. Okay, so this time is -1/2, right? And the solution, the point of solution, right? That's going to be e to the power -1/2. -1/2. And the -1. And here you go. You see, that's the solution. That's the solution. Okay. And do we understand that solution? Do we understand that solution? Right? The input, right? That's the input. How much is it? E, root E over E. This is root E over E. And the output is -1/2. -1/2. Okay. So understanding the inside and out of these equations is super duper important. And I hope I have achieved that goal and for you. And please take your time to study these lectures and do your homework. If you have any questions, please don't hesitate to let me know. Last but not least, just to make sure you get these, let me just mark it over here. Okay, so this black piece is e to the power of -1/2. Okay, and the red piece is -1/2. Input, output. If you reflect on all of those, if statement equations we have done, right? From trig equations, to exponential equations, to logarithm equations today, don't they all have the same idea? Aren't they consistent? The only thing that's different are the rules, right? The rules are different. The rules are different. All right, so without further ado, I will see you guys next lesson. Thank you for watching.